So let's switch to computer science here real quick and do some fun stuff. I said that a unitary system, one particle, has a binary output, right? And that a binary system, 2, has quad outputs, okay? And that a ternary system, 3, has 8 outputs. Now, the ternary system is the 3 transitional planes. So here is the 3 transitional planes that create 8 quadrants of space. So this is the 3 that creates 8. 2 that creates 4 is the particle in motion causing a difference in density above and below this line, the plane of density. And so you have a duality, right? A binary system with quad outputs. So the Dirac's equation that sits above this plane of density, as defined by the Hamiltonian and the Lagrangian, are the quad outputs to this binary system. And it's a single particle in motion that creates that binary system, right? So you have a single particle in motion creating a binary system. That binary system has quad outputs that create a ternary system of 3 transitional planes creating 8 outputs. So that is Shannon. How do I know this? How can I prove this to you very quickly? Well, in computer science, in all of computers, you're being lied to. They say that our computer is based on a binary system, but it's not. It's a unitary system. This is the way your NP connection works, right? You have this line going in and this line going out, and an orthogonal one here, which is a gate. And when you fire this, it closes and doesn't let it through. And when you don't fire, it allows it to pass. And so the output of this junction is 1 or 0. It either allows the electron to pass or it doesn't. It's 1 or 0, and that's your binary system. So now you're saying, well, wait a minute, you just said it was a unitary system. Well, it is. This is one line. Think about it, if you will, as a light, just to make it simple in your own mind. Right? One light can either be on, right? The light can be on, or the light can be off. No problem, right? So we have 1 or 0, but it's still one light that's either in one of 2 positions. So our computers work this way. And this is actually a unitary system. It's a single system that's either on or off. So once a unitary system has a binary output. So when they say our computers are binary, that's what they're talking about. So what does that mean? Well, you've heard of quantum computing, right? So what are they doing in quantum computing? Well, that's a binary system creating quad outputs. So think of it as 2 lights, okay? Well, what do you get when you go from 1 light to 2 lights, right? They can either both be on, right? Or they can both be off, or one can be on and one can be off, right? And it can be one of either. So what does that mean? So they've created the same binary, all on 1 and all off 0, but between them, one can be on and the other one can be off, and you don't know what those are, right? And this is qubits, actually, right? So what is the difference between quantum computing in reality and regular computing, unitary computing? Well, regular computing has 1 light. It's either on or off. That's a binary output. So a single unitary system has a binary output. Now, qubits, quantum computing, ooh, right? Well, it's actually just 2 of those systems. And they can either be both on or both off, so you still have your binary system. Or, and in between those, one can be on and one can be off. And this is where you get this whole quantum entanglement thing. Well, if one is on, then the other one must be off, and you don't know whether one is on or off until you test it, and woo, right? Yeah, they're lost. Here's the problem. They can't control the quad outputs to the binary system. Okay? Why? Well, because all you have is one on and one off, and one must be opposite to the other. Okay? So this is how computers work. Unitary system with a binary output. Qubits, right? Quantum computing is a binary system with quad outputs. Okay? So they say this is the future of computing, but they're wrong. Why are they wrong? Well, because you can't control this system with a binary input. Okay? You can only create the system, but you have no interaction with it. There's no way for you to control this system unless you go to a ternary system. Imagine this with 3 lights now. 1, 2, 3. Okay? Now you can use the functions of the orbital field that I've been talking about to control the system. This is how it works. All 3 can be on, right? Or all 3 can be off. And so you have your binary system. Okay? You following? Now, you can also have 1 light on, but you have 1 light in 3 positions. So you can have 1 light, or 1 light, right? And this is in between all on or all off. Well, then you can also have 2 on in 3 different positions. In between all on and all off. So if you're going to build a qubit system, you can't control it because you have no idea what's happening. And you can't force anything to happen, right? So why is this, what am I talking about here? If you have a ternary system, you can have all on or all off, still creating your binary system. But inside that binary system, you can have 1 light on in 3 positions or 2 lights on in 3 positions. And if you use this, if you use your intelligence, your logic, to create an orthogonal connection between the 3 of these, then you can have 1 on or 2 on relative to each other in between your all on and all off binary system. And this gives you an orthogonal connection here and here and here. And those 3 orthogonal connections are how you control the qubits. Only, as we've decided, shown you up here, right? A unitary system has a binary output. A binary system has quad output. This is quantum computing and where they're at right now. And a ternary system has 8 outputs. And those 8 outputs are 1, 2, 3, 4, 5, 6, 7, and 8. And if you build your model for your ternary computing in this way, then you have 3 controls. Well, what is that? Technically, in computer programming, these 3 are tetrahedrons. And they represent in physics the eigenstates of mass. You can control, right, your ternary system. So these are qubits, these are bits, and these are Qbytes. So when they get done fucking around with, there I went and swore again. When they get done screwing around with their binary inputs, which give quad outputs that they can't control, you will have to switch to a ternary system, which gives you the binary system, and inherent to the ternary system, you can align these, and when you align them, you give levers which allow you to control the quad outputs to your binary system. And these are technically eigenstates. And these eigenstates are how you will control quantum computing. But it's not quantum computing with qubits, it's quantum computing with Qbytes. And this is all Shannon. So if you have, and this is in the book, or at least most of it is, but, you know, humans interface in base 1, and we calculate in base 10, because it's easiest for us and we're simple creatures. But like the orbital field is in base 9, based on thirds in quad outputs, then, right, this is 0 third and is 1. 3 would be the ternary hardware that I just defined here. So if you compute, now again, they say that we're computing in binary. We're not. We're computing in unitary systems. So if you, right, qubits are binary systems trying to compute in quadratic outputs. If you jump to ternary, you get 8 outputs, which allow you to create eigenstates, which allow you to control the Qbytes. So 1, 0, 3, 0 thirds is our understanding. 3, so this is the interface for humans. This is the human interface. 3 is the hardware, right? And I know I scribble a lot, but it's not what it looks like that you should be paying attention to here. It's what I'm telling you and how it works. 6 then is the software interface. And this is going to come out as 6n plus or minus 1, which is what I'm about to explain to you next. And then 9, which is 3 thirds, is how you're going to communicate. One, 3, 6, and 9. Interface, hardware, software, communication, transfer. And the only way to reach Shannon's limits is if you communicate in base 9. And I'll show you how if you want. But this is a 1, 3, 6, and 9 orbital field function that defines how each of these things are going to go. And 6n plus or minus 1 is where we're going to finish this video, because 6n plus or minus 1 is the primary equation to find all prime numbers. And I'm going to show you the equation to find all prime numbers here now. And that this is actually, I've talked about NP, or P equals NP. This is NP complete. So when you understand the software is running on NP complete, and your hardware is running on ternary, and your interface is unitary, and you're communicating, transferring the data in 9, you can reach Shannon's limits here. You can reach, well, basically omnipotence here in NP complete if you run a ternary system, which creates a binary all-in or all-out system with orthogonal connections between these, giving you the eigenstates that allow you to control the system. I know, they're telling you can't know this. They're telling you that you can't control qubits and that they're lost in it and it's some crazy thing that can't be understood. They're wrong. They're just looking at it incorrectly.